Welcome to the lecture 11 of our molecular spectroscopy series. Today we will analyze how the physical environment of a molecule directly modifies its quantum mechanical energy levels and changes the absorption spectrum that we measure experimentally. Let us begin with a standard absorption experiment. When an incident beam of light denoted as I0 passes through a sample cuvette, only part of that light emerges. This transmitted intensity is represented as IT. If we calculate absorbance and plot it against wavelength lambda, we obtain an absorption spectrum. Here we consider the example of conjugated molecule 1,3-butadiene. The most important feature of the spectrum is the peak position. This peak is defined as lambda max. Lambda max represents the wavelength where the probability of electronic transition is maximum. As experimental physicists, our goal is to understand why lambda max shifts when we change the molecular structure or the surrounding solvent environment. When a molecule experiences external physical perturbations, the entire absorption band can move along the wavelength axis. We classify these movements into two major spectral shifts. First, if the absorption maximum moves toward a higher wavelength, we call this a bathochromic shift. In simpler laboratory language, this is called red shift. Whereas, secondly, if the absorption maximum moves toward a shorter wavelength, the phenomenon is called a hypsochromic shift. This is commonly known as blue shift. To understand why these shifts occur, we must examine molecular orbitals. In a molecule at a ground state, electrons occupy quantized energy orbitals. The highest energy orbital that still contains electrons is called the HOMO, the highest occupied molecular orbital. The lowest empty orbital available for excitation is called LUMO, the lowest unoccupied molecular orbital. During photon absorption, an electron moves from HOMO to the LUMO. The energy of the absorbed photon is exactly equal to the energy difference between these two orbitals. Therefore, lambda max directly reflects the HOMO and LUMO energy gap. These orbitals represent real distributions of electron density. Because of this, they are extremely sensitive to the external electric fields. Solvent molecules possesses dipoles that create surrounding electrostatic fields. Depending on interactions, a solvent may stabilize either the HOMO or the LUMO. If the solvent stabilizes the HOMO strongly, its energy decreases. If the LUMO remains unchanged, the energy gap increases. Alternatively, if the solvent stabilizes the excited state LUMO, the energy gap decreases. Thus, the environment directly controls the photon energy required for absorption. We now connect this idea mathematically. According to the Planck-Einstein relation, delta E equals h multiplied by c. Divided by lambda, energy and wavelength are inversely proportional. If the HOMO-LUMO energy gap decreases, the required photon energy becomes smaller. A lower energy photon must therefore have a longer wavelength. As a result, lambda max shifts to a higher value. This produces a bathochromic shift. We call this phenomena as a red shift. Recall the visible spectrum picture. The red region contains the longest wavelength and lowest photon energies. Therefore, whenever lambda max increases, the absorption moves toward the red side of the spectrum. This terminology applies even when absorption occurs in the ultraviolet region. It is universal spectroscopic convention. Now consider the opposite case. If the environment interactions stabilizes ground state strongly, the HOMO energy decreases significantly. The energy gap increases. From our equation, a larger energy gap requires a higher energy photon. Higher energy corresponds to shorter wavelength. Therefore, lambda max shifts toward a smaller value. This is hypsochromic shift. Because shorter wavelengths lie toward the blue and violet region of the visible spectrum, this shift is universally called a blue shift. Any movement of lambda max toward lower wavelength is classified under this term. Finally, let us discuss absorption intensity. Until now, we focused on peak position, but the peak height is also important. Changes in intensity are called hypsochromic effects, while wavelength shift describe energy changes. Peak height represents transition probability. A small energy gap often increases transition probability. This produces high molar absorptivity and stronger absorbance peaks. Conversely, a large energy gap reduces transition probability and lowers intensity. By analyzing both spectral shift and intensity variations, we obtain a complete quantum mechanical understanding of molecular behavior. Thank you.